We covered several topics in data analytics. So in that course, we understood how we deal with data, how to analyze it, but not from the machine learning perspective. The main distinction between data analytics and machine learning is that the learning part. How it works, just like I describe it here. Last week we covered this topic, regression for machine learning. How the system works, as you see. In regression analysis, we construct the model, right? Construct the model. And then, based on this model, we just make some predictions, all right? That means somehow there is a data here, some data, maybe two-dimensional, and then distributed in such a way, all right? Assume that this is our independent variable, x, and this is our dependent variable, or change. So by looking at the x values, we just try to predict the y value. So we try to understand the relation between them. Building the model means describing the relation. In linear regression, we said that this relation is described in a formula, in a model, in a way that some coefficient, let's say c times x plus some bias value describes the relation. So this relation here, if it is in such a relation, it's a linear regression. So it's supposed to be related like, let's say, this way. It makes a line, right? So this is the definition of line, right? So this is the slope, in fact, and this is the bias value. What is bias? Bias means that if this is 0, B is something. For instance, here it may be -1. Okay. Maybe 0 or any value. That may be a bias or may not. So this describes the relation. So in regression analysis, again, we just define the model and start predicting new values. The new values by looking at this model we described, right? Therefore, guys, this is regression. But when it comes to machine learning, we evaluate the model. That means that using all these data, we develop this model, and then some other data, right? Okay. Let's say this one. This somewhere here. Okay. So by just looking at this, sorry, right? Yes. We just guess the y value. So this is our prediction. Then there is a difference between these two values, all right? So we evaluate the model and then make predictions. Then go back again and again and again, make modifications about this coefficient and this bias, right? This is the learning part. For this, here in regression analysis, or from the data analytics perspective, we say that we analyze the data and develop the model, or deduce the model. But from machine learning perspective, or using machine learning terminology, we say that from this sample data, this is the sample data, we just take traditionally 80% of it and use it for, what is it? Training, right? That means that analyzing data. And we just, after this training, introduce the model develop the model. And then we use the 20% of this data for testing, okay? During this testing, we just test the predictions and understand the errors, the level of error. See how we can measure the level of error. For instance, in fact, that data was in the sample set at the beginning. What we just put it into this set randomly, all right? Then use it. That means we in advance know the output, the real y value. So that between the real, actual, let's say, and predicted y values, we can measure the distance, the difference, right? Either using this one, mean squared error, or r squared. So by looking at this, we can train the data. I mean, we can make modifications. This is the learning part, all right? This is the main difference. the rest, the model part is the regression part. We've already covered last semester in the data analysis course. So guys, also we covered last week the types of linear regression. Types of regression. One was this one, linear regression. We give some examples. All right. And if there are more than two variables here in regression analysis, we call these variables independent variables or features. But this one is the dependent one. So this is the one that we are trying to predict. Therefore, if there are more than one independent variable, we just apply multiple linear regression. It's exactly the same thing. Worry about this is the linear part. So if you add new features, then it becomes multiple linear regression. It's very easy to understand. Okay, it's the same thing. But as it gets beyond 2, we cannot. I mean, beyond 3, we cannot visualize it actually. All right. But if this relation is not linear, just like this one, instead, let's say it's quadratic or something like this, okay? It becomes a non-linear relation. Therefore, we apply polynomial regression. There may be one or more than one variables again, independent variables, going this way. All of them may be related in some different ways. For instance, this one is related directly linearly, right? X, only x, there's no power. But here square, cube, goes to 0, right? So actually it's a polynomial formula or equation. Therefore we apply polynomial regression. Actually there's no difference. Logically we apply, okay? So, for example, this, as I said, it can be multiple. And we also told how we will choose the right regression is obvious. Okay, guys. And also, in large data sets, I also told something called this thing, I cannot pronounce it, heteroscedasticity, something. We need to check for this to understand whether our model is acceptable, good or not, right? For this, we either check visually if it has a funnel shape, it has this undesired feature, or statistically by applying these tests we can decide it. So here is an example, for instance. It's a real data set, as I told you, taken from the internet. Actually not the internet, but deep learned library has it ready to use, right? California house prices. So here I just for visualization purposes I just took two features only. Here I believe one is the price, the other is the square house, I don't remember. So when we draw it, as you see, there is a relationship between them, but actually, if we draw the residual plot, we see some shape. If you see such a shape, it indicates that there should be something fishy, something some problem in your model. Therefore, it indicates that, but it just indicates it. You cannot tell it exactly what is the problem, etc. You need to apply the other tests and try to understand. Here, for instance, we can see that shape, so we can say that our model is a little bit unreliable. Therefore, it is so natural because, as I said, I took only two prices, yet there are other features affecting the price, but I just left them out. So it is natural to see something like that. If there is no problem, the scattering here should be around 0, right? Just like this, I'm assuming that this is here, so it should be scattered around 0. And as I said, that since we know the actual label of the data and use it for testing, okay, and training also, we call it supervised learning. One of the supervised learning methods is that regression analysis and machine learning. You can supervise the model, the result, the prediction, right? You can supervise. Okay, I predicted this, but is it correct? Or what is the level of error by measuring mean square error or square, etc. Is the training. So guys, I just covered all this stuff last week, but I just omitted this type of regression analysis.
So last week I was studying about this subject and I saw different subject. It says regularization for overfitting. Can you touch a little because I didn't get it at all?
Yeah, I'm gonna talk about it. Okay, last week I said that we're going to cover this separately. Okay, so this is part of regression analysis, machine learning, regression, machine learning through regression analysis. We can say this is another type, but today we're going to cover this logistic regression. Okay, it's a little bit more complicated. And also we'll talk about the regularization, etc. Okay. So any questions about regression analysis or machine learning based on regression analysis? Any questions? If there are no questions, let's go into logistic regression. Okay. So here guys, now, well, before that, let me go back to regression. And you see, here, the data may be categorical or continuous, all right? For instance, in housing example, house prices example, the data, yeah, the y value and also the x value or the other features, maybe, or are continuous, right? Continuous. Not only 1, 2, 3, or categorical like gender, for instance, or education level, etc. Okay? This is continuous, but on the other hand, we can also apply logistic regression, regression analysis on some categorical data. Okay. See? Yeah. All right, guys. If the data in hand is somehow binary or categorical, what it means, to predict the dependent value that you're trying to predict, it may be yes or no type, categorical, okay? Like whether it is a spam or not, disease or not, right? Pass or fail. In such a case, you can use logistic regression. Actually, that logistic name has nothing to do with logistics. Instead, we just use a log function, okay? Logarithm function. Therefore, it is called logistic regression. There's no logistics related anything about it. Okay. Well, I'm not going to talk about all this stuff, but if you take some values, let's say between 5 and 7, whatever, and increment it by small steps. But every time, for instance, if you increment and some dependent value, depending on this one, let's say this is x, and another value, y, like this one, you end up with some line graph, like this one, right? But instead, you just take the logarithm of it, and also here, it becomes something else. I mean, something else. In logistic regression, if you understand this relation, I mean, taking the logarithms of this, and also, if you remember the normalization normalization topic we covered, we may normalize the things between 0 and 1 values, right? And at the same time, if you normalize the values, either you applying some max-min approach or standard deviation approach. Remember the Z value approach. If you just squeeze it between these values, all right, it becomes something like this. Let me show you. See, this is the linear regression. If it goes this way, for instance, by taking the logarithm of the values, it becomes something like this, okay? Therefore, here, if at the same time, this is just the view that we just took the logarithms, okay? Every value is logarithm. But if you at the same time squeeze or standardize it between these intervals, okay, it becomes like this. See? So these are the independent values, and this is the dependent value, telling that the y value will be always between 0 and 1, depending on this one, right? So in this case, actually, since it is between these 0 and 1, we can understand it as a kind of probability. Okay, probability, not a distinct value, distinct output, but a probability. For instance, if you're talking about predicting the student grades, it is a regression, typical traditional regression problem. Okay? Predicting student grades based on the working hours and distance from school, blah, blah. You can add many different features. In this case, it is a regression problem. But if you try to predict the outcome as not the grades, but instead whether the student will pass or not, okay? Pass or not pass, okay? So it becomes a binary question. At the end, you can decide, depending on some threshold value. For instance, you can apply logistic regression and say that C is the threshold, the lowest grade to pass, which is 50, for instance. And by looking at the predicted values, you can decide whether the student passes or not. So you just convert it into some discrete value, pass, not pass, okay? At the end. But it still has nothing to do with the probabilities, right? Probabilities. Just like the fuzzy logic. Remember the fuzzy logic thing? There, we also somehow related the output with some kind of probabilities, although there were no probabilities there, but instead it was something that it is called the membership weights. Not probabilities, but membership weights. So here, when we apply logistic regression, now we are somehow interested in the probabilities. This is a binary, either binary 0, 1, pass, fail, or spam, not spam kind of problem, or it may be multiple, but we always deal with or involve in some probabilities in outputs, all right? The outcome is some kind of probability, we can say, right? Because why? Well, because we squeezed it between these intervals, I mean 0 and 1 interval, right? We just squeezed it. We first took the logarithm and then standardized it actually into this interval. Then it becomes some S, I mean, just like you see here, S shape. S shape. Of course, the shape of the form of this shape graph will change. I mean, this is only an example. It can be something like this. Or like this. I mean, it may be different. Another S shape. It may change, okay, depending on the values, but it's still an S shape. All right? As I said, its form will depend on the values, the relation between the input and output values, but it's still giving us the probabilities between 0 and 1. How it does it? But actually, since we apply a logarithm, there comes the natural logarithm, actually. And because of that, we use that eigenvalue. Where is it? Yeah, this one. That eigenvalue, E value, okay? It comes from Euler's number, CE. It comes from the natural logarithm, okay? So we call it the sigmoid function, since it looks like a sigma function, okay? This is why it's called sigmoid function. So in logistic regression, instead of applying this type of equation, we just represent the things using such an equation, okay? Sigmoid function, right there. So here, W is the slope, etc. as it goes this way, but here is E value, which is something around this value, and Z is sigma Z is our output. So we just give the values, the Z value, and get the sigmoid position. I mean the position of that Z value, on this curve, all right? If the Z value is here, so the output is here, right? So it is between 0 and 1. Very nice. So then we can say that the probability of having this value is that.
This formula is transforming the linear regression equation to probability value?
Kind of, yes. But as I said, that in the linear regression, the values are continuous here. It may or may not be continuous, but at the same time, the output is binary or categorical output. All right, but remember that the output is categorical, pass, fail, spam, not spam, but instead of giving spam or not spam, we just give the probability of it, okay? So if it is larger than 0, then we can say that it is spam. For instance, this part is spam part, okay? So logistic regression gives us the probabilities, not the values, but the probabilities. So it's very useful in this means. See, this is the values we took the logarithms, but here when we squeeze the standard, see, it comes something like this. So this is the equilibrium point. This point, see, for this value, for instance, here, since it is a standard distribution, the 0 value, but it may be different. I mean, it may be shifting left to right or whatever. So in this case, probability of being spam or not spam, for instance, is equal, right? So actually, we call it, or I call it, the duality position. Duality. This position is exactly the duality position. You can be either there or there, but both are true or both are wrong. I mean, it's equal. The probabilities are completely equal. Right? So guys, again, here, although I simplified it here, the Z value may be something like this, okay? Again, I can be using many different parameters or independent values, but at the end, we just apply it this way. I mean, use them as the power, because, you know, taking the power of something here, the relation is not linear, right? Therefore, we just, it should be some power of something, either negative or positive. So we apply the logarithm, and then we just convert it into the power form, right? See, we just took the logarithms and then converted again to reach these values. This is why we use E here for angle. If you're interested in the underlying mathematics, I just give you the hints on why that E value or value is here. This is the reason. I mean, since we took the logarithms, but there the logarithm is not base 2 or base 10 or whatever. It stays natural logarithm. Okay. Then we use that 2 point something value as well. Okay, guys. All right. So then we can compare the linear regression and logistic regression here. If the output type is continuous, we apply linear regression. Okay? And we use real numbers as the output interpretation. I mean, the output will be a real number, the student grade or something. Okay? All right, guys. For instance, assume that we're asking we collected data about the weather conditions, the temperature, humidity, etc., for this region, and for the annual data, on the annual data, we applied some regression analysis. There may be many different, multiple factors or features we want to include. For instance, the humidity and the temperature, and maybe the winds, whatever, right? So, in this case, we may ask the question whether, the level of, let's say, rain. What will be the level of rain, for instance? We just wanted to predict the level of rain, all right, for tomorrow or today. So by developing on the sample set, we developing the set, the model, we just apply the model and predict the value, right? So it gives us some figure, some real number
indicating the amount of rain for today or whatever. But when we are interested in whether it's going to be rainy today, will it be rainy or not, independent of the amount of rain, okay, then it becomes binary, right? Either rainy or not rainy. So we apply logistic regression, okay? This is the case. But now we are just asking whether it's going to be rainy or not. If it is so, if it is going to be rainy, what is the probability? Okay? So we're interested in the probabilities in this case. So it will give us some value between 0 and 1. Okay? If you go back to this one, this value plus 1 divided, see, 1 divided by this one. So it just actually gives the probability, right? And formulating it this way just squeezes it between 0 and 1. 0 and 1. So here, house prices, here spam prediction, or the amount of rain you may try to predict here, or we just look for whether it's going to rain or not, what is the probability. All right. So this is the binary case. There are only 2 outputs. Okay. These are the student working hours or study hours, and this is the pass fail 0 or 1. Okay. 0 represents fail. So if you write such a program, very simple, as you see, very simple. Create some data. Alright. Then first train it this way. Okay. You just tell that you're going to use the logistic regression model and fit x and y values. See? Here you provide the independent value, the variable, and then the dependent one, right? And telling the program, the library, use this regression model, logistic regression, then fit it. That means the training, okay? So it just generates the model. Generates the model by looking at all these data. It can be thousands of them, right? And after training, we just predict using some x value and measure the accuracy score. What is the accuracy? So it gives us the training accuracy, and then we just apply prediction for 5 new students, or what? New students studied for 5 hours. Okay. We just give the value and ask the prediction. But now, in terms of probabilities, we just plot it and see the result. Okay. It gives us something like this. So here, there are only a few data. 1, 2, 3, 4, 5, 6 data, and 1 new value. So it trains the model using sample data. Now this is the new value. Okay, you can change it. So if you go there, let's see that. Yeah. If you go there, I believe that this is the example we're talking about. Okay. Bu ne ya? Ne oluyor ya? Çalışmıyormuş. Neyse, buradaki şeyin aynısı. Burada verdiğim örneği. Okay. I just wanted to change the values and see this difference. Right. So it gives us some like if you change the training, I mean the sample set here. Right, this is the sample set. This is the X value. These are the. See, these are the labels actually. Labels. Since we provide the labels in advance, this is called supervised learning. This is part of supervised learning algorithms. Okay. Right, guys. Logistic regression. Here, this is the binary type. But if there are more than two variables, we just call it multinomial logistic regression. Just like this one, we just give the color code for the fruits, all right, and the weights. This is the weight, this is the color code, and we say that this is fruit. For instance, we can add some watermelon, which is much larger, heavier, right? But still red or green. Okay. Then you say that this is watermelon. Okay. So using these data, it just tries to predict the fruit type. We just give the weight and color, then it gives us the name of the fruit, okay? Here are the labels, okay? Here are the labels. But at the end, as you see that these are all categorical. I mean, if you label apple, for instance, as 0 and banana 1, pear 2, this way, right? It should be numerical, right? It defines no relationship. I mean, it's not ordered somehow.
Yes.
It doesn't mean that pear is larger than apple or something like this. Okay, it's just a categorization, but it should be in numerical form, right? To be able to train the data set. So after training based on this data set, you just question the fruit type based on new weight and color values.
Unordered.
Here we give this value for weight and color code, and it gives us banana. Again, here these are categorical, and also these are categorical, right? But here, as you see, it is not binary, 0, 1, pass, fail. Instead, there will be many different categories of the output. Therefore, this is called multi-nominal or multi-categorical logistic regression. This is the only distinction between them. All right. Okay, guys. This is the basics, the main idea of the logistic regression. But now we're going to get into some very interesting, important, very generic topics under this title, but it is also valid and used for the other types of machine learning algorithms. It's used everywhere. You'll understand it very soon, but we're going to give a short break. If you have any questions, just ask. Okay? Any questions?
Hocam burada kumandayı
Tabii ki. Yetişeceğim. We use different algorithms, different approaches for different questions. We just use different approaches, representing different approaches, these algorithms, right? But the main workflow, which describes the machine learning, is the same, just like I described. You get a data set, and depending on the data and the question, just like this one, whether you're related or request some probability type of information, whether you need to predict a binary value as spam or not spam, or probability, or a number, direct number. Depending on the output that you're interested in, you choose the correct method, right? Data analytics method. Some of them, as I said, are counted in data analytics. Also, logistic regression is one of them somehow, but we didn't cover last semester. But regression in general is a data analytics method. So the distinction between the standard data set machine learning is that training or well, not training actually, but the modification part, right? I mean, fine-tuning the model. That means that at the beginning, you'll remember that I told you the real output is a machine learning algorithm is the model itself, right? If we're talking about machine learning, that it is different from traditional data. Let's say data. Traditional automation type algorithms. This data is the input, okay, and we just produce some out and then store, etc., etc. But different from this one, the traditional automation type of workflow, we just feed the output back. How? Well, actually here, first we evaluate the result, and then after this evaluation, decide how to modify the model, okay? How to modify the model. So let's say modify the model or tune it, whatever you call it, and then feed it back, change the model, right? Therefore, the output itself becomes input somehow. But here, not directly the output, but the evaluated output, or whatever you call, is fed back to the system. So what is this output? Actually, this is the prediction, right? Our predictions. So this part makes the whole system learning, right? Up to now, we told about different types of algorithms, actually regression, linear and logistic regression type of algorithms in machine learning. We'll cover the other algorithms like support vector machines on this side. But in all algorithms, the main workflow is the same. And I said always, we just check the results. That means measure the error, right? Measure the error. And then apply modification, fine-tune the model. Now, I need to describe this part, how we modify or how we apply the measured error into the system, how this modification works. So this is a crucial, very principal part of machine learning. You need to understand it. It's independent of, somehow, mostly, independent of the underlying analyzed algorithm, maybe logistic regression or linear regression, whatever. But we apply always the same logic, okay? So how we apply this? Actually, we just measure the cost, okay? That is, we need to compute somehow the cost of this error, okay? So here we just measure the error, and then say that the cost of this error is that, okay? Therefore, because of this error, we just penalize the system. We apply some penalty. We apply some penalty to the model. We just tell the system, okay, you are trained this way, so using the 80% of the data you trained and then tested with 20%, but the result still has such a level of error, so this is the cost, so I penalize you. Okay, so applying this penalty means actually modifying the system. I mean modifying the model. Okay? So this is the learning part. Okay, you learn this. Now you behave as the model, the system, accordingly. Accordingly, we change the parameters. That means that, for instance, if we're talking about a linear regression type of application or logistic regression, which is actually the same. See, on the E part, E, Z. That Z is actually, or Y, it is the same thing, okay? Y actually is something like this, okay? It may be linear or non-linear. Doesn't make any difference, all right? Doesn't make any difference. See? It is the sigmoid function. So that Y is actually this one. It can be anything. Multiple regression type of, or maybe polynomial type of model description. So, teşekkür ederim. Therefore, therefore, that means that this one has, just like I gave you the formula here. What is it? See, it can be something like this. Okay, this. So these B values, or here, don't get confused with this B and that B. Here I used C and that B, whatever. Here, this is the B value, or this we can say that it's constant. Okay, so we just change the B values, okay? We just fine tune them. These are the coefficients describing the model. And this part, actually, this part, the sigmoid part, is just for putting it in the logarithm form and squeezing it between 0 and 1, all right? This is used for this. The real model is actually here, in this Y part, or Z part, or whatever, right? So we just apply these penalties to these B values, or these coefficients of the model. These coefficients of the model. We change these coefficients. Well, this is called regularization. Okay, regularization is this somehow. Not exactly, but we can say mostly. This is regularization. We need to regularize the features somehow, because, well, we're going to cover all this stuff there. Okay, so let's try to understand that learning part. Here, the loss penalty mechanism in machine learning I'm talking about. There is a loss function or cost function, okay? It is the same. Loss function and cost function are used interchangeably in this literature. So it describes the error, right? So in machine learning, iteratively, during training, and also later on, if you keep learning and learning and learning, during training and also during the learning period, if it continues after the system started deployed, okay, you may still continue learning by accumulating the results, so then enlarging your sample, then apply a new model. Bakın yeni mesela chatbotlar çıkıyor. Chatbot bilmem kaça bilmem kaç. İşte bilmem 4 bilmem ne oluyor aslında. Şimdi sizin chatbotlarda falan veya neyi kullanıyorsanız, tabii oradaki sistem, Logistic Regression gibi başka türlü sistemler falan fark etmez. Lojik aynı yer. Bakın, lojik aynı. İşte her girenle beraber sistem yeniden eğitilmiyor, öyle bir şey yok.
Ama bu data toplanıyor. Bu sefer mesela daha önceki kurdukları modele, yapıya göre ya şu feature'ı da ekleyelim, şu bilmem neyi de yapalım gibi şeyler de yapıyor olabilirler. Modelde değişiklikler de yapıyor olabilirler. Hiçbir değişiklik yapmasalar bile ellerindeki data seti büyüdükçe büyüyor. Dolayısıyla biz böyle bir data setini eğitirken tabii data setinin büyüklüğüne bağlı ve modelin karmaşıklığına bağlı olarak dünya kadar computation yapıyoruz değil mi? Yapıyor yani. Dolayısıyla arkadaki işte hardware ihtiyacı buradan kaynaklanıyor. Bunu sizin her girdiğiniz datayla beraber böyle canlı real time yapmıyor. Modelde kıvırda zıvırda yaklaşımda hiçbir değişiklik yapmasa bile datayı biriktiriyor. Sonra update yapıyor. O yeni bir release çıkartıyor. Arkadaki yapıyı değiştiriyorsa eğer, tamam mı? Orada modelde bir takım değişiklikler yaptı, bir şey yaptı falan. O zaman ne bileyim ben 3.2 falan değil de 4.0 çıkıyor. 4.0'ın bilmem ne reasoning şeyi çıkıyor. Reasoning ile ilgili mesela parametreler ekliyor. Diyor ki benim bu yeni modelim, bak reasoning ile ilgili parametreler ekledim. Öğrenmede reasoning ile ilgili şeyler ekledim. Tamam, buna karar verirse bu böyledir. İyi ama niye böyledir taraflarını ekledim. Onunla ilgili de data topladım. Onunla eğittim. Bu daha reasoning konusunda daha etkin. Öbürü ise daha böyle bilgilere erişimde falan daha etkin olabilir. Değil mi? Ne bileyim. Yani bu yapay zeka modellerinin öyle anılıyor ya. Spesifik belli konulara özel olmasının da nedeni bu aslında. Diyelim çizimle ilgili bir şeyse bu. Tamam mı? Çizimle ilgili datayı topluyor, bilmem ne yapıyor ağırlıklı olarak. Ona dönük bir yetenek kazandırıyor. Tamam mı? Diyelim artla ilgili bir şeyse art. Sadece müzik. Sadece olmayabilir ama ağırlıklı olarak müzik. Yani topladıkları feature'lar filan ona göre seçilmiş. Dolayısıyla farklı alanlarda uzmanlaşmış yapay zeka geliştirmiş oluyor. Anladınız mı arkadaki lojiyi? Yani bunu anlamanız önemli. Şimdi bu genel modeli anladıktan sonra you can put any algorithm in the system. Okay? Here we just put the logistic regression. So we just describe the function this way as a sigmoid function. But the system, the generic workflow is the same. Train the model using logistic regression, blah blah. Then do predictions on the trained model, okay? And measure the error. But we still assume that we know the correct answer, right? That means that this is a supervised learning system, labeled. Therefore, when you say a chatbot, for instance, do this, do that, it gives you a result, right? But then you say something, you respond. Come on, you missed this part. This is not correct. I'm not sure whether it works this way, etc., etc. So you train it. You just give the labels, right? The labels. But it may not be in a binary way. I mean, this answer is correct or this answer is incorrect. Instead, you may provide the level of correctness or the satisfaction level, etc. So it just tries to figure out how satisfied you are with this answer. Okay? And I believe that you encountered, it gives you two different answers and wants you to choose one of them. Which one is better, right?
Training.
It's just training. So it just gets your answers, applies some natural language processing methods, and tries to understand your satisfaction level. And from that, instead of deducing some 0-1 result, whether the answer is correct, incorrect, it just tries to understand the correctness level or something like that. Some model runs behind, right? This way. So through this, it just labels the answer now. Labels. That means that it can now measure the error. Actually, you provide the error, the satisfaction level, right? You provide this. So Therefore, it can go and apply this logic. I mean, based on this measuring error measurement, I mean, the loss function or loss value or whatever, it just decides about the penalty and applies this penalty and refines the model. Okay, but again, it is not actuated. It is not done real time. Instead, it just collects this data, and then trains again from the scratch using new data. And now it's a better method. I mean, system they got. Okay, they either release 3.5, 3.56, whatever, or if they change the underlying method, the approach and everything, if they add new extra features, I don't know. Now it becomes chat. What is it? Chat GPT 4.0.
4.5.
4.5.
There is an endless collective progress, I guess.
Yeah, it reflects the progress actually. But since it jumped from 3 to 4, I can easily say that the underlying approach, the method in the 4th version has some radical changes, new features, I don't know what. And you know the DeepSeek just appeared, right? DeepSeek. For instance, their source code is open. You cannot see the underlying method, the approach and everything in ChatGPT, but with OpenSea you can check it. Well, even if you can download it, you can download the whole model, but you cannot use it because you don't have such a hardware data in hand, so you cannot process it. I mean, you cannot train. Either you have this the behind and the underlying logic completely, the code itself, right? You cannot use it, but at least you can understand their approach, what they use, or what are the mechanisms, etc., etc. It's very good for the scientists or researchers. It's invaluable. Okay? So this is the logic. You need to understand that loss penalty mechanism or cost penalty mechanism because it is valid for almost all machine learning algorithms. This is the way of learning. Think about a little kid or any kitten, huh? Kitten. How it learns? It jumps, runs, etc., and always it hits somewhere, falls down, right? Tumbles, and with every action, it learns something, right? It hurts. It is cold, it is hot, it is wet, whatever. And gradually, it tunes its abilities, I mean, its behavior, its decisions, actually. The decisions. Should I jump from here to there or not? This is a decision, right? So a kitten, a small one, cannot jump there, just falls down, tries again and again and again, then finally decides that I should not jump if it is that distance. Okay, kind of thing. Okay.
So is it similar, like unsupervised learning and self-learning?
Yeah, self-learning. Yeah, self-supervised learning. Somehow. See, if it is not supervised, that means that it says unsupervised learning. Then you need to label it, right? You need to. This is the only distinction. I mean, this is the main distinction between these two machine learning types: supervised, unsupervised. In supervised method, you provide the result itself, so that the system can measure the prediction error or the loss value, cost value. Okay. Size parantez içinde bir şey söyleyeyim arkadaşlar. Şimdi benim bu yaptığım çalışma geçen dönemde biraz hani konusu olduğu şeyde bahsettik. O dedim ya uncertainty üzerine çalıştım falan filan diye. Onun değerli bulunmasının nedeni ne biliyor musunuz? Aslında ben bakın zamanımı ona harcamak istiyorum da kesinlikle zaman ayıramıyorum. Üzerinden 3 sene geçti. Halbuki şunun farkındayım. Ben bunu ilk anlattığımda böyle uluslararası bir şeydi yani internet üzerinden böyle bir gruptu yani research grubu olarak. Yani o gruba dahildim. Yabancılar işte Amerikalılar bilmem falan. Orada bahsettiğimde bir de kafa buldular. Yani kafa bulmak gibi yani. Washington Üniversitesi'nden bir profesör ukala herifin teki. O işte ben dedim ki bak budur yani. Budur bak burada prediction uncertainty tahmin ediyorsun filan. Bu machine learning'de filan da dedim çok kullanışlı olabilir. Yok ya dedi, anlat o zaman nasıl kullanılacak falan. Ben dedim ya ben şu anda onun üzerinde çalışmıyorum. Ben başka bir şeye uyguluyorum bunu. Hani bunun uzmanısın madem bunun üzerinde düşün filan falan. Karambole geldi gitti. Aradan herhalde 7-8 ay geçtikten sonra o toplantıda olan yine İTÜ'deki hocalardan hocam işte profesör o aradı. Böyle yapay zekacıları işte toplayıp onları konuşturan bir şey var. Türkiye Yapay Zeka Platformu'na öyle bir şey yani bir kuruluş işte yani kurum değil de öyle bir platform. Her sene bir iki şey yapıyor. Böyle toplantı düzenliyor. Dünyada da 5-6 tane insanı çağırıyor. Onlar orada online konuşuyorlar falan. Dedi ya ben geçen dedi hatta dün bir toplantıya katıldım işte onu davet etmişler Türkiye'den de. İşte bir şeyler anlatmış falan yapay zeka ile ilgili işte şey. Amerika'dan dedi katılan birisi vardı dedi. Sizin dedi anlattığınız şeyi neredeyse dedi birebirine anlattı. Yani nasıl kullanıyorlar? Benim söylediğim şu arkadaşlar ben diyorum ki bakın cost diyorsunuz bunu diyor. Şimdi ya burası bu seviye olmayabilir de hani kendimi tutamıyorum şimdi. Tamam mı? Hani ama anlayacağınızı düşünüyorum. Bakın cost diyorsun. Aslında cost ne demek ya? Sen cost'a göre karar vermemelisin diyor. Benim iddiam bu. Oturup bunun çalışmasını yapman lazım. Yapamıyorum. Cost'a göre değil, riske göre karar vereceksin diyorum. Risk. Bu modelin kökten değişmesi lazım. Tamam mı? Yani genel bu öğrenme metodunun değişmesi lazım. Çünkü şöyle sen cost'u değil, riski hesaplayacaksın. Risk dediğin nedir? Her kararın içinde belirsizlik vardır. Değil mi? Cost'la karar verilmez ki. Şöyle karar verilir. Biz cost'la mı karar veriyoruz sadece? Yani şöyle düşünün arkadaşlar. Piyango bileti alıyorsunuz değil mi? Tersten düşünün. Kazanma olasılığına göre mi karar veriyorsunuz? Ha? Neye göre piyango bileti alıyorsunuz? Yani şans değil. Neye göre yani? Ha, o karara yol açan şey nedir? Sana diyorlar ki işte şimdi kaç para bilmiyorum. Yıllardır da almam da. Piyango bileti falan. Yani diyelim ki 100 lira atıyorum. 100 lira da yoktur. Daha fazlasıdır.
600 lira.
Ne diyorsun ya?
Çeyrek yüzde
O ne lan? Neyse
Tamam,
işte.
olsun.
Diyelim 100 lira olsun. Tamam mı? 100 liran gidiyor. Kazanma olasılığı ne? 7 rakam var değil mi? Buyurun. Evet buyurun.
Sandalye bakıyorduk da.
Bakın. Bak bir sürü sandalye var.
Alabilir miyim?
Hayır, dersini mi böldünüz ama?
Evet, o yüzden kusuyorum.
Şimdi 7 hane var değil mi piyango biletlerinin? 7 hane. Kaç rakam? Her biri yani şey tabanında, 10 tabanında değil mi? Desimal. Yani bu ne demek? 7 üzeri 10 demek değil mi? Ha? 7 üzeri 10 ne demek? Hesaplayın. 7 üzeri 10. 7 diyorum. Evet 7 hane. Değil mi? Piyango bileti 7 hane midir? Herhalde 7 hane. Birkaç milyardır.
28 milyar 247 milyon
Güzel.
200.
Demek ki arkadaşlar sizin piyangoyu kazanma ihtimaliniz nedir? He? 1 bölü 28 küsür milyar. 1 bölü 28 milyar diyor. Ya 1 bölü 28 milyar ihtimal verilen bir şeye para verilir mi ya? Ha? Bakın olasılığı söylüyorum size. 1 bölü 28 milyar olasılık olan bir şeye para verilir mi?
282 milyar pardon.
Neyse 280 daha da vahim yani. Verilir mi öyle bir para? Peki niye alıyorsunuz?
Şans diyorlar.
Şans demiyorlar. Bak orada başka bir şey var. Ya çıkarsa? Ya çıkarsa tarafına bakıyorsunuz değil mi? Demek ki sadece cost değil. Cost belli burada. Costunuz 100. Peki kazanırsam ne kazanacağım? bilmem ne kadar. Şimdi o zaman tabloyu şöyle kuruyorsunuz. Kazanma, kaybetme. Değil mi? Kazanmanın maliyeti ya da getirisi, kaybetmenin maliyeti ya da getirisi. Değil mi? Beraber bakıyorsunuz. Sadece maliyete mi bakıyorsunuz? Getiriye de bakıyorsunuz. Öyle olmasaydı piyango bileti satılmaz. Dolayısıyla siz diyorsunuz ki kazanırsam da işte ne bileyim ben 10 milyar kazanacağım. Neyse. Tamam 10 milyon kazanacağım. Dolayısıyla 100 lira bölü daha doğrusu 10 milyon 10 milyar neyse kazanacağımız 40 milyar bölü 100 senin kazanç katsayını gösteriyor değil mi? Bu kadar kat para kazanıyorsun. Ve onu olasılıkla çarpacaksın. Onun gerçekleşme olasılığıyla. O sonuca göre hareket ediyorsun sen. Demek ki arkadaşlar sadece maliyetle karar verilmiyor değil mi?
Hocam bence ama bu kişi bunu size böyle söyleyen kişi bunun farkındadır. Başka bir amacı olabilir. Yani
Bilemem.
başka bir şey düşündüğü için
Bilemem.
size bahane olarak bunu söylemiş olabilir.
Bilemem. Yok farkında da olmayabilir. Yani benden daha mı zekiler? Hayır. Hayır değiller. Hayır değiller. Ne münasebet?
Düşünmüyorlar mı aslında?
Olabilir. Yani başka bir şey düşün. O başka bir şey bulur. O onun aklına geliyor, benim aklıma geliyor. Bu da benim aklıma gelir. Yani kimse benden daha zeki değil kardeşim. Ya da herkes ne kadarsa ben de o kadarım yani. Kendinize böyle bakacaksınız. Ne münasebet? Ben ondan daha iyiyim bilmem neyim falan gibi değil. Bu benim düşüncem. Düşüncem budur. Bunu değerlendireceksin. Bu herkes için her durumda geçerli. Bu zeka yarıştırma bilmem platformu değil burası. Bir fikir var burada. Bunu konuşuyoruz. Bu kadar basit yani. Dolayısıyla ben üzerinden yürüyemezsin. Olmaz. O salaklık olur. Şimdi dolayısıyla ben de diyorum ki buradaki cost fonksiyonunu ona göre tarif edeceksiniz kardeşim. Bunun içine uncertainty'yi de katıp, tamam mı uncertainty'yi? Buradan bir risk hesabı yapacaksınız. Yani risk, burada sizin uncertainty'niz, tamam mı risk? Bunun peki böyle karar verirsem diye bir de cost ilişkilendireceksiniz buna. O cost'la beraber decision çıkacak diyor. Tamam mı? Ya da yani cost, burada cost diyoruz, öbür taraf milli piyangoda kazanç. Öyle karar vereceksiniz. Eğer öyle karar verirseniz daha iyi olur diyorum. Bu oraya uygulanabilir diyorum. Benim iddiam buydu. Tamam mı? Ama üzerinde hala çalışamadım. Hala yapamıyoruz. Adam dedi ki, hatta çizdim. Neredeyse ya. Ben dedi video linkini atayım size. Attı. Asabım bozuldu ya. Benden neredeyse işte bir seneye yakın sonra.
Aynı adam mı? Washington Üniversitesi.
Hayır canım başka. Herifler 7 kişi falan işte akademisyenler bilmem ne o alanın babaları şirket kurmuşlar. Herif onu anlatıyor. Biz ne yapıyoruz? Şirketin yaptığı sizin machine learning modellerinizdeki uncertainty'yi ölçüyor. Bunun için de para alıyoruz. Lan benim yaptığım işi yapmış. Bunun için şirket kurmuş. Benim anlattığım şey yapmış. Bir de grafikler çiziyor. Neredeyse benim çizdiğim grafiğin aynısını çizdi herif ya. Sanki. Hayır canım benden araklama falan olduğunu düşünmüyorum. Ya, o da düşünmüş olabilir gayet normal. Herifler göremedi. Anlatabildim mi? Dolayısıyla işin bu tarafı çok enteresan. Zaten bunlar üzerinde çalışıyor. Yani yeni bir şey bulduk. Yeni bilmem iyileşti. Bunları buluyorsun işte. Yani. Böyle şeyler buluyorsun. Anlatabildim mi? Çünkü burada mesela uncertainty'nin ölçülebilmesidir. Artı bunu bu modelin içine, bu sistemin içine genel olarak, bu illa machine learning olmak zorunda değil, başka her şey olabilir yani. Bunun içine nasıl uygulayacağımızı matematiğini çıkarmaktır. Okay guys, but the generic learning approach or workflow is something like this. Therefore, we can say it involves in the cost or loss function and also the penalty. Now comes the regularization. For instance, in linear regression,
regression, we just use the MSE, for instance, the loss measure or error measure or cost measure, whatever you call it. For classification type of things, we use logistic regression. We use log loss, and how about penalty? Well, using the penalty, we regularize the system. Regularize the system. Okay. Regularization adds a penalty to the cost function, loss function, based on the size of model's weights. Model's weights. What are the weights? When we say weights, we are talking about these coefficients. Okay. The terms, the terminology may differ. Okay. In statistics, they directly call it coefficients. Okay. Or in mathematics. If it's a linear regression, we just call it, or we can call it the slope of the line. So the terminology may differ, but actually we can point out the same thing. So the penalty term we're talking about. Penalty helps. Now, that was Nazir's question. That helps us to prevent overfitting. What we say overfitting? Well, our model
Overlearning?
tries to fit the model to something which in fact does not fit. Okay? But we just force it to fit. So it overfits. While it was not fitting, actually, it just tries to overfit and fits and gives you a prediction which is not correct. Okay? So you need to apply some kind of regularization to prevent from this kind of overfitting. Okay? This is overfitting and this is regularization. This is why we use or why we need regularization. So the final cost function is the loss times loss plus the penalty. But we also give some lambda value which we can adjust. Okay, that lambda value. Using this value, we can smoothen the penalty. I mean, it may be small or large, so we can decide about the level of penalty we're going to apply. Okay? All right, guys. Herkes anladı mı bunu? So, lambda controls the strength of regularization. Higher the lambda, more penalty. In simpler methods, we prefer this one. So it just prevents overfitting. But if we apply less penalty in more complex methods, it creates risk of overfitting. Okay. Right. So we need to balance it. For instance, here I just give an example. We're assume that analyzing the shipping costs and the fees. Okay. Here is the fee of the package or whatever, right? And you apply a fee for that. This is the fee, weight and fee. So trying to predict, just like the house pricing example, we're just trying to generate such a model. So here, you may add some penalty on the luggage weight, right? This is the coefficient, the weight, right? So you just try to balance it actually. If you apply too high penalty, for instance, that means that it just takes the coefficients to, I mean, it pulls them towards zero, okay? Towards zero. You just reduce it. So you just somehow reduce the effect of the coefficient, okay? Effect of the coefficient. So if it is too high, it gets, vanished, becomes zero. Okay? That means that you do not ask for any fee for some person or luggage. Okay?
But if it is too low, it doesn't help much. All right, so you need to balance it through regularization, and you'll decide about it by playing with the lambda value. Okay, guys. So regularized loss is that the error plus that penalty term, all right? Now we just regularize the loss itself, the cost itself, by applying some penalty. Okay, so there are two types of regularization. One is called loss and ridge, the other one. They use different mathematics. You see, as I said, we fine-tune the model. How we fine-tune the model? That we apply some mathematics. We just apply some formula. I mean, we just add all the coefficients or the weights, okay? Square them and add them up and multiply it by lambda. Okay, this is the ridge method, for instance. But instead here, instead of squaring them, it just gets the absolute value and adds them up and then multiplies again. Very close to each other, but they give different results, okay? So let me show you some examples. All right. So let's start from the beginning. This is our first example. Now it runs and produces this. If you play with these values, it changes, all right? Or if you add some extra values, let's say, for instance, 5 here, okay, and say 1 again, it changes again, right? See now what happens. You see the form, the shape of this curve has changed, but it is still sigmoid, right? Still sigmoid, just like I described it. It's still between 0 and 1, but the shape has changed, right? So if you add more data, you'll get a better representation of your data, right? So the output, when you run, the output will give you the predicted probability. Here, for instance, probability of passing for hoop. Here I gave some value, new value. Let's say the new value here, new data. Here, new data value is, let's say, 7. So I'll just put it here. Okay. For now, I'm asking if the student studied that long, 7 hours, what is the probability of passing or failing? Okay. Now it gives another prediction. Here it is right there, and says that this is the probability, 93%. Okay. But if I reduce it to, let's say, 3 hours, it gives you. Here now it is here. See the same. See the form of the sigmoid function didn't change because the training data is the same, right? We didn't change it. Just gave a new data, and it just predicted based on the new data. This is 3, so it gives this value. So it is something 3 something %. Okay.
Yes.
Less than 21. Okay, so this is how it works, all right? You got it?
Yes.
Any questions about it? I believe that you understood the mathematics behind. Her ne kadar size matematiğine girmeyeceğim diyorsam da kendimi tutamıyorum. Çünkü anlamanız için gerçekten işin bu tarafını da yakalamanız lazım yani, diye düşünüyorum. Tamam mı? Yani neden böyle oluyor ya? Sihir mi? Ne sihir abicim? İşte bu yani. Logaritmasını alınca zaten yani alın mesela dediğim gibi birden bilmem 10'a kadar rakamları alın, işte bir fonksiyon yazın yani. Şeyde bias 0 olsun. Tamam mı? Bildiğin her regression şeyi yazın. Nasıl olsun? Birden 10'a değişiyor. Bu da işte birden bilmem kaça kadar değişiyor. Dolayısıyla onun size şeyini verecek değil mi? Eğimini verecek. Şimdi bunun grafiğini cart diye çizersiniz. Plot diyeceksiniz değil mi? X bu, Y bu diyeceksiniz. Cart diye size çizecek. Değil mi grafik? Ondan sonra arkadaşlar ödev. Bunu deneyin. İşin matematiğini anlamanız açısından. Yani X ve Y vereceksiniz. İşte lineer olarak bunlar ilişkili olsun. Tamam mı? Bias da vermeyin. Tam sıfırdan başlasın hani. B değerini vermeyin. Şu tarafı vermeyin yani. Şu sıfır olsun. Sadece böyle bir şey. Y eşittir 3x, 5x bilmem neyse değeri değişiyor. X'e bağlı olarak. Diyelim 3x ise size değeri 3 olan yani eğimi bir şey verecek yani. Değil mi? Şimdi bunun plotunu çizin. Ondan sonra x'in logaritmasını, y'nin logaritmasını alarak aynı değerleri verin. Yani x'i değil, logaritma x'i verin. Çıkana bakın. Sigmoid bir şey elde edeceksiniz. Ama 0 ile 1 arasında değil. Tamam mı arkadaşlar?
X ile Y arasında.
X ile Y arasında yani. Yok. Y'nin işte maksimum minimum predicted value'ları arasında. Kaç çıkıyorsa. Tamam mı? Ona işte şu formüle koyarsanız onu 1 bölü bilmem ne derseniz o zaman da 0 ile 1 arasına sıkıştırmış oluyorsunuz yani. Hikaye bundan ibaret. Tamam mı? Peki niye yapalım böyle? Çünkü 0 ile 1 arasına sıkıştırınca bana probabiliteyi vermiş oluyor. Yüzde kaç olasılık? Onu söylemiş oluyor. O yüzden bunu yapıyoruz. Tamam mı arkadaşlar? Oturdu mu bu konu?
0 ile 1 arasını almıyor değil mi ödevde?
İşte 0 ile 1 arasını almayın. Onu alırsanız zaten Logistic Regression yapmış olursunuz. Tamam mı? Yani sadece o log'un nasıl etkilediğini görün diye istiyorum. Tamam mı? Ha bununla oynayabilirsiniz. Datanız mesela bu dataya göre şey değişecektir oradaki sigmoid. Mesela datanızı Gaussian üretin. Tamam mı? Gaussian bir data üretin. Yani hani x değerlerini. Tamam mı? Size Gaussian verecek şekilde üretin. Gaussian. Bakalım nasıl bir sigmoid oluşuyor. Filan gibi yani. Bununla oynayabilirsiniz. Peki bu örnek böyle. Let's jump to the other one. Saat kaç oldu? Ne kadar zamanım var ya?
Yarım saat.
Yarım saat.
Peki. Let's take this example. What is this? Yeah. It's a larger one. Okay. We use the iris data set here, but I think only 2 features. Okay, sepal length and sepal width. So I apply logistic regression. Okay. By looking at one feature, we decide about the other feature, right? I just simplified it. So we just classify and draw the decision boundary. If it is larger than this, it goes, it is this category or that category. Here, I just wanted to draw the decision boundary at the same time. If I run it, you'll understand what I'm talking about. Okay, so depending on this value, how the value changes, you see? So this is decision boundary. It's pretty close to support vector machines. We're going to come to this later on, okay? So, let me show you again. This is the training set, okay? This is the training set's results. So, 80% of the data, okay? Now, I just test the model developed using this training set on the test set. As you see that it is a smaller sample size, you see, smaller. Right, so we can compare, and then we just compare the results and measure the accuracy, okay? As you see, the accuracy is 1, 0, that means that perfect. Okay? So this example gives this idea. And what about the third one? What was it? I don't remember. Let me see. What is this?
here, these are the education levels, and these are the incomes. Let's jump. Let's see if I jump or not. Here, since it is how many? 5-dimensional. It just gives the regression model. Okay. This gives the regression model. I cannot draw it. Okay. But here, you can find a reasonable, reliable reason after some certain numbers of iteration, you couldn't reach the limit. I mean, it couldn't find a reliable result. So probably I need to increase the training, number of trainings. Fit function.
Bir tane sandalye salonu olacak.
Olmaz. Olmaz. All right. Whatever. So this is another example. Okay. This example is about multinomial. Okay. Logistic regression. Here, multinomial. There are more than two independent variables or features, right? So let's see the third one. Yeah, this is another multinomial. Here, C, bananas equals etc. gives us the answer. Again, I cannot draw it and show it graphically, but here it predicts it as banana. But again, multi-class was always use multi. Okay, banana. If you change here in the values, let's say the color is not what is that, red, 0, 1, no, what is red? Red is red is 1. Let's say it is yellow. Okay, so it is 1. Let's see what happens. Again, it gives banana. Let's say it is 3. Green. Again, it says banana. So stupid, you see, because there is only 5 samples. That's it. But if we change, let's say, the weight to something 65, it gives what? Apple. Now it says apple. Whatever, right? So it is multinomial, more than one categories in the output, but still it decides based on the probabilities, all right? Based on the probability. As you see in the sigmoid function, if the probability is higher than 0.5, you can say that it passes, it fails, whatever.
you make the decision. But in multinomial case, you need to check the highest probability, okay? The highest probability. All right, guys. Just like we did in fuzzy logic. We computed the weights, and at the end, we decided about by looking at the highest weight. Okay. But at the same time, different from this one, it just gives the answer in a categoric way, right? It either says banana or apple or whatever. But in fuzzy logic, it says it is that percent of banana, but that percent of apple, right? This is the difference between this one and fuzzy logic. Size bir şey söyleyeyim mi? Şu söylediğim bu kavramları çıkın. Şurada 4. sınıf bilgisayar mühendisliği çocuklara sorun bakın hangisi.
Taner işçi var hocam bilgisayar mühendisi. 3. sınıfta gidecek o da. Daha yeni böyle Python'a başlıyorlar.
Seneye bitirecek, seneye bir daha sorarsın. Fuzzy logikle bunun arasındaki farkı şimdi siz anladınız değil mi? Anladınız. Mesela bunun amplitüdü neden farklı, ne anlamı geliyor? Bu neden fuzzy? Bitirsin, o zaman bir daha sorarsın. Gene bilmiyormuş. Evet. Okey. Peki diğer örneğe geçelim. Şimdi geldik regularization örneklerine. Şuradaki regularization'a bir bakalım arkadaşlar. Bu örnekte ne yapmışım? Bu örnek muhtemelen notlara koyduğum örnektir. Regularization. Evet, şurada bir örneğimiz var. Budur herhalde. Yalnız şeye dikkat edin. In Python, instead of using lambda, we use C. Okay? It's the same. Actually, C equals to 1 divided by lambda. Okay? So we just invert it. Somehow invert it. Okay? But it's the same. In logic, the approach is the same. So, this way, we can play with the C value. If we increase the C value, we apply a stronger regularization, right? Because lambda becomes smaller this way, right? No, lambda increases, yeah. If we give a large value like 1,000 or something, it means we apply almost no regularization, okay? So here is the comparison between L1 and L2 methods. In this example, guys, let me show you the example. Where is it? Regularization. Let's see. Okay. See, actually, I applied that formula. What was the formula? Here, this was the formula. These two. I just applied these formulas, computations, to lines, okay, and see how it changes the lines, the structural lines, okay? Çocuklar korktunuz. Buraya dönün. Bu örnekte bakın burada ne yapıyorum? Absolute value'sunu alıyorum ve ekliyorum. W1'in, W2'nin. Çünkü burada 2 tane feature var. Tamam mı? 2 feature'a da şeyleri ekliyorum. Absolute value. Burada ise onların karelerini alıp ekliyorum. Dolayısıyla lasso ve reach yöntemlerinin ikisini de uyguluyorum. Lasso nasıl bir şey yol açıyor? Reach nasıl bir şey? Şimdi buna baktığımız zaman aslında şunu anlatıyor bize bakın. Gördüğünüz gibi bakın şunda kenarlar köşeli hale gelmiyor. Tam tersine yuvarlak hale geliyor. Tamam mı? Reach metodunda. Ama ortadaki değerler, yani sıfıra doğru giden değerler kayboluyor. Yok oluyor sıfıra doğru giden değerler, kaybolmuş oluyor. Burada ise sıfıra doğru azalıyor ama kaybolmuyor. Tamam mı? Ya da Anladınız? Bunu gösteren bir örnek bu. Eğer görebilirseniz. Gerçi burada da I just commented it, described it. See? Here in this first one, nothing gets zero. Nothing gets zero. But here, you see, it just gets vanished, right? So in the third set, I just applied the same thing to the iris data set again. Here, let me show you this. Yeah, this one is a larger set. Again, we apply different, both methods of regularization and check the results. Check the results, compare them. Okay. And there are the results. This is the graphic. So this is the difference between the data. Okay. See, it just, for instance, in the rich regularization, it just omitted, cleared that part and that part. So as you see, the rich method somehow eliminates the outliers, right? Outliers. Somehow, if you assume that that part, the edges,
Orange.
are outliers, it just helps getting rid of some outlier values, all right? Okay, guys. And also, let me show you the final one. Here, again, I apply L values, but here I just change the C value, the lambda, 1 divided by lambda, okay, C value. And you will see how lambda affects the weights, the weights, the futures, all right? I just plot how many futures I have, whatever, 5 different futures. You'll see by applying different values of C, how it changes. You'll see the coefficients, the values of these futures will change. Let's see how it changes. Here, see the animation. Closer, but yeah, at the end it reaches to 0, yeah? Here. So here, guys, as you see, some of the values, some of the features gets vanished. For instance, here, that orange one, or the yellow one, or whatever, they just get lost. They became 0. So we do not take into account. If you make this one 0, that means that you just cleared this out, okay? You just throw this feature. So in your model, that value, that independent variable feature, is not evaluated or counted any longer. You just omit it, okay? So using this method, L1 method, Lasso method, helps you choose the correct or the most significant features. Okay? You can reduce the number of features involved, okay? Using this method. On the other hand, if we apply the other one, the rich method here, this one, check this, the same 5 features change this way, right? They get closer, but never 0. How many? 4. Yeah, there are 4 different features, so maybe 5. Yeah, 5. Another one, green one. All 5 features are here, but we just smoothen them, but they never reach 0, right? We just
Approach.
keep all the features. So in complex models, you can use to reduce some of the features using the L1 method. You can decide about it, okay? That means is for penalizing, etc. You can, you need to apply regularization, and during regularization, you can choose either methods, depending on the data set. And you need to check if you're working on a project or something, you need to apply both methods and check the results. Which one works better, okay? And also you need to tune the lambda value, the penalty value, the C value. All right, change the C value, now it gets better, and then you decide, okay, for this type of data set, that C value is the best, and this method is the best. Then you train your data, all right? After deciding about all these parameters, you decide all these parameters, C values, etc. Then you train your set and test your set, and now it is ready. It is a trained model. We just save this trained model and use it later for prediction. We're not doing it here. Actually, bakın arkadaşlar, şöyle çalışır, onu da anlamanızı istiyorum. Şu ana kadar hiç bahsetmedim ama keşke söylemiş olsaydım, aklıma geldi. Şimdi tabii bu training zaman alıyor. Biz 3 tane 5 tane üzerinde yapıyoruz. Size derste daha önce de söyledim. Diğer derslerde yaptığım gibi hani burada canlı yapamayacağım bazı şeyleri. 3-5 datayla yapabileceğim. Çünkü deli computation'la yapılıyor bu training. O zaman büyük data setlerinde biz 3 saat, 5 saat, bir gün, 5 gün bekleriz. Tamam dedim. Niye söyledim bunu?
Nasıl çalıştığını anlatmış.
Şimdi dolayısıyla bir data setini aldınız, karar verdiniz, parametre ve train ettiniz. Şimdi her prediction için bir daha train edip, şeyi üretip, modeli, ondan sonra prediction yapacak haliniz yok. Günlerce, haftalarca bekleyerek, değil mi? O zaman ne yapıyoruz? Bu library'ler train ediyorsunuz. Ondan sonra train edilmiş halini saklıyor. Save ediyorsunuz. Tamam mı? Yani training için ayrı program yazıyorsunuz, prediction için ayrı program yazıyorsunuz. Anladınız mı? Bizde ikisi beraber burada. Anladınız? Projelerinizde öyle olmaması lazım. Yani tez yapacaksanız makine öğrenmesi üzerine train edilmiş, yani etmeyi sağlayan programınız ayrı olacak. Train edildikten sonra o modelin train edilmiş halini saklayacaksınız. Aynen şu anda ChatGPT'nin bilmem nenin yaptığı gibi. Train edilmiş halini train ettikten sonra sakladı. Şimdi bizim her şeyimize, girişimize, bilmem neyimize prediction programı cevap veriyor. O modeli kullanarak. Dolayısıyla prediction programı da ne yapacak? Modelimi bir yükle, train edilmiş modelimi. Tamam, şimdi hazırım. Sor soruları diye çalışması lazım. Anladınız mı? Yaklaşım. Tamam. Bana her şeyi öğrendiniz ya. Makine öğrenmesinde bir şey kalmadı. Size bir şey söyleyeyim mi? Bugün anlattığım başlıklar makine öğrenmenizi yani anlamanızı sağlayacak temel başlıklardı. Bundan sonra tabii supervised learning'i konuşuyoruz. Aslında supervised'da buna yani çok farklı. Bundan sonrakiler şeyleri değiştireceğiz. Arka plandaki o underlying algoritm değişecek. Logistic Regression yerine başka bir şey kullanacağız. Başka tip bir şeyin peşinde olacağız. Başka bir yaklaşımla bilmem ne yapmaya çalışacağız. Ama hep öğrenme ve bilmem ne işimiz bu mantıkla gidecek. Loss function, cost function, penalty bilmem ne. Herkes anladı mı makine öğrenmesini? Var mı anlamıyor? Harbi söylüyorum. Var mı anlamıyor?
Şu an ben tam anladığımı düşünmüyorum. Gidip şey yapacağım. Sindirmeye çalışacağım.
Anladınız da yani öğreneceksiniz. Size bu derste ödev vermiyor. Çünkü ödeviniz belli. Bir konu anlatıyorum. Onun örneğini yapacaksınız her ders. Regression yaptık. yapmış olmalısınız. Bir örnek. Şimdi Logistic Regression yaptık. Bununla ilgili bir örnek yapacaksınız. Ayrıca o log fonksiyonu nasıl etkiliyor onu görmeniz için de öyle basit bir örnek verdim. Yani ödev verdim. Onu da bakın nasıl bir sigmoid'e ulaşıyor. Tamam mı arkadaşlar? Evet, soru varsa alayım, yoksa dersi bitiriyorum. Yoruldum ya.
Kaçta